Now let's take a look at the general Diptera life history. So we're going to spend the rest of this unit talking about those species that are important to animals. So those species of flies that are especially important to animals. The way that these flies can be important to animals is how they attack or affect the animals and their environment. These species can be hematophagous, meaning they feed on blood. So you can break up that word. Hema means blood, phagous means eating. So they are blood feeders. They may also be flesh feeders, or feeding on decomposing material, or they might feed on open wounds of animals. Maybe they feed in fecal matter. If you've ever been to a horse barn, you know that there are houseflies and things flying all over that poop all over the time. Maybe they feed on garbage in the environment. Maybe they feed in sewer systems or on other rotting organic matter. But they are in the environment. So because of this, flies are considered very, very veterinarily important because they can have a solid impact on the health and well-being of animals. Many of these species, like I said in one of the other lessons, they inhabit aquatic or semi-aquatic environments during the larval stages. So remember, that is either full liquid, so in ponds and puddles and things, or semi-aquatic, so decomposing material or fecal matter or drains. So mosquito larvae, they are immersed fully underwater. If you go and you see puddles or you go and you look in ponds, you're going to see these little wiggling flies or little wiggling larvae underneath the water. Those are mosquito larvae. Blowfly larvae, or the brachyceran larvae, tend to live in decomposing material. There are also flies that we call moth flies, which I'll talk about later on in the semester. They live in drains, so that's pretty liquidy but not full-fledged, always underwater. Rat tail maggots, you may have seen some of these. They live in sewers or at the bottom of garbage cans. So these look like brachyceran larvae, except they have a really long tail at the end. At the end of that tail is a sphoracular opening. So basically they're using this long rat-like tail as a snorkel. So they live underwater, but they can still breathe. So they're all over the place when it comes to these liquid or semi-liquid environments. So their larval anatomy will support their living in this environment. As we get into each family and each species, I'm going to talk about the exact anatomical adaptations and modifications that are necessary to live where they live. But just know that each larvae has these adaptations that allow it to live in its preferred environment. Now, the females of these species may or may not be able to produce a batch of eggs under certain circumstances. So because these veterinarily important species often are blood feeders, they're often tissue feeders, things like that, we have two categories of flies that we deal with. They are autogenous and anontogenous. So a female that is able to produce a batch of eggs without a protein meal, so without, say, feeding on blood or feeding on flesh or feces or garbage, these are called autogenous species. So autogenous species are able to produce eggs without intaking more protein as an adult. They basically save up all this protein from their larval stage, use that stored protein to produce that first batch of eggs, then they have to go off and feed in order to get more protein to produce more eggs. So autogenous females do not need a protein meal. If you break up that word, auto means self, genus means the beginning of, basically like Genesis, you know. So they're able to use their self in order to produce eggs. The opposite of this is anontogynous. So anontogynous organisms need a protein meal before they can produce their first batch of eggs. So a lot of blowflies, a lot of mosquitoes, they have to blood feed. They have to go feed on rotting material. They have to feed on fecal matter. They have to get protein into their diet. They have to break it down to those amino acids, and then they use that diet-based protein in order to produce eggs. Okay, so autogenous and anontogynous. These are two major ways that females will produce these eggs. And as we go through these different species, I will tell you if they're autogenous or anontogynous. What I want you to do is think about why is that important and how can you use the information of autogeny or anontogeny to maybe kill off some of these specimens. All right. Probably the most important aspect of fly behavior is the host-finding mechanisms of both blood-feeding and carrion or filth-feeding flies. There's been a lot of research in this area, and it basically breaks down into two things. Flies use both visual and olfactory senses in order to find their potential hosts. So they use both sight and smell to find what they're going to feed on. Let's talk about the olfactory cues first, because these are the ones that people have really focused on. A very common olfactory cue used by blood-feeding insects is carbon dioxide. Why do you think that is? Think about what you do when you breathe, right? We're breathing in oxygen, we're breathing out excess CO2. So, if these blood feeders, say, need a living organism in order to feed on blood, in order to get the protein that they need, they can sense the amount of CO2 in an environment. The higher the amount of CO2, the more likely it is that a living, breathing, respiring organism is sitting right there, and therefore they probably have blood that they can feed on. So these flies will monitor the amount of CO2 in the atmosphere, and they'll figure out where they are, either downwind or upwind, of a potential host. Okay, so that exhaled CO2 will serve as a cue for recognizing and locating potential hosts. Now, this is the basis of things like dry ice traps or bottled carbon dioxide when you're trying to improve trapping for different flies. You're basically trying to trick that olfactory system of these flies into thinking that there is a warm-blooded organism there that they can go and feed on. So they'll follow that CO2 and get stuck in those traps. Now, there are other chemical cues that insects use, especially flies. They use things like lactic acid or cadaverine. These are things that are given off by decomposing materials. So there are certain species that will be highly drawn to that. And if you couple that with CO2 or you couple that with other things in the environment, you can make a very effective trap to monitor and to collect these species. So this is one of the major reasons why we go into what are these different flies attracted to. So we can design traps. So if you're trying to design your own trap, say for your ranch, for your farm, for animal management, you want to look into what are they attracted to. And if you put that into a trap, these flies will come in droves. Now, the principal means by the way most repellents work then is by blocking this olfactory system. So I'm sure many of you have put on some sort of off or what is the big one? Avena, like Skin So Soft, right? And you spray that on when you're going outside or to the lake or to the river so you don't get mosquito bites. Yeah, the way that works is it's blocking this olfactory mechanism in these flies. So there's really strong substance in the best mosquito repellents. It's DEET. These really strong substances are going into the antennae of these flies and binding with the neurons in those antennae so that when they're flying around, they can't smell anything else. Now, have you ever gone into a room and you smelled something really strong, right? Or like you're in an elevator and somebody has worn the worst perfume in the land and it's super strong in there and your eyes are watering and you kind of get a headache. For the next few minutes, you can't really smell anything else, can you? Right? So you're out and about, you're not really smelling anything. That's because it's the same sort of action. That really strong scent has bound to those neurons and has really overwhelmed your olfactory system. So that's basically what we're doing with these insects or with these flies, is we're overwhelming their neurological input so that they can't smell that we are delicious to eat. Neat. Okay. Now, other flies, certain flies, are very sensitive to black body radiation outside this visible spectrum to humans. So we can't really see this type of radiation, but certain flies can. Okay, so they're really attracted to it. Now, there's not a lot of work that has been done on this, but there is some. And I think I have a video up for you on eCampus that sort of gives you an idea of what this looks like. But it's been theorized that these females will sense warmth against a very cool background, kind of like a thermal vision camera. So if you think about, big old pasture, it's nice and sort of cool and greens in this thermal camera. And then you have a cow right in front. That's going to be orange and red and giving off heat. So these females can look at that heat-producing organism, say, that's warm-blooded. They couple that with olfactory, and they're able to find this cattle. Okay? They may also look into the size and the shape of hosts, depending on the species. So they're trying to visually recognize their preferred host or their preferred species. So this is why some organisms will only really land on horses and cows, but not on humans, or not on dogs or cats or other small mammals. Okay, so they're looking size, shape, body heat, plus all this olfaction. Now, the female also has some extra duties, if you think about it. She needs to be able to identify an environment that is suitable for her offspring. So she's going to use both her olfactory system and her visual cues to identify such areas. So let's talk about Ocarin feeders now. So carrion flies, they need to find a dead animal to lay their eggs on. That's kind of small in a big environment. So the way that this olfaction works is it looks like olfaction is their primary cue, although odor may not even be detectable by humans, okay? So they're going to be looking or smelling for these dead bodies. Similarly, face flies, they can appear at cattle dung pats almost immediately after those cattle defecate. So they are perceiving these chemical cues to find these potential egg-laying or oviposition sites. So most flies can perceive these chemical cues at levels orders of magnitude greater than humans. So they're smelling things that we can't even perceive in the environment. Now, organisms use primarily one of two major reproductive strategies when they're doing this sort of thing. And think back to when I talked about oviparous versus ovoviviparous versus pupiparous flies, right? Okay, so a few dipterans are known as K strategists, and in this case, K represents the carrying capacity of the environment. These flies have longer life cycles, produce fewer offspring, and are very, very influenced by density-independent mortality factors. Okay, so a pupiparous fly would be a K strategist. Long life cycle, fewer offspring. The mortality for the most part for the mortality factors is things like weather, okay? Things of that nature. So density independent. More commonly, though, in flies, we see the R strategist. So R denotes an instantaneous rate of population increase. In R strategists, they have a large number of offspring, so they're likely oviparous. Okay? Each individual has a relatively small chance of survival, but because there's 300 of them, there's a pretty good chance that some of them will make it. So these flies exhibit very, very rapid growth, very short life cycles, very high mortality rates, attributable mainly to density-independent factors, okay? All right, now, with that sums up our basic overview of Diptera. Okay, up next, we're going to start looking at individual families. Let me know if you have any questions.